So we continue with an introduction to Markov chains and hope to finish this in this particular video lecture. So just to summarize from last time, or not even to summarize, but to sort of play a little bit with the evolution of the marginal distribution. What we started with in the discussion of marginal distributions is the idea that the probability that at time t plus 1, the realization of the state xt plus 1 is equal to y is it's a summation of possibilities, of the following possibilities: that at time t, the state xt was some x times the probability that at time t plus 1, the state xt plus 1 is equal to y, given that at time t, the state xt was x, and these come out of the stochastic kernel or the transition matrix. These are the pxy's, right? And I sum across all possibilities for what the state is at time t. So what's happening here is, so I have a time t here and a time t plus 1, and I have a bunch of states. And I'm interested in the probability, in the marginal, that at xt plus 1, the realized state is some specific y, right? So the y can be realized by a hop from any of these states, x1, x2, all the way through xn, right? And the marginal at time t was, this had a certain probability, so you can just say, probability xt is equal to x1, probability xt is equal to x2, and so forth, right? And then there are these transition probabilities, that the probability that xt plus 1 is equal to y, given that xt is equal to x1, so that's p x1y, p x2y, all the way through p xn y, right? So these are, in some sense, different paths by which the state at time t plus 1, the realized state is y, right? So I add up these probabilities. In some senses, I'm adding up the probabilities across these paths to get this. And then using our notation that ct plus 1 is a 1 by n matrix that captures the marginal distribution at time t plus 1, this is the probability number sitting in the yth place of the 1 by n matrix ct plus 1. So that is the marginal distribution, which is a 1 by n matrix CT, its dot product with the n by 1 matrix P dxy, which is the transition probabilities from the n different states x1 to xn, yeah, to the state y, right? And then if we collect these for all the realizations, all possible realizations y at time t plus 1, we get this sort of, you could say it's a first order difference equation, which is ct plus 1 is equal to ct times the transition matrix M. The transition matrix M has as its yth column the p dxy matrix or vector, right? And then using a recursion from here, we get that ct plus 1 is equal to the initial distribution C times the matrix M raised to the t plus 1, right? Or to write things slightly more cleanly in terms of simply t, we say ct is equal to c times m raised to the t, right? And subsequently we interpreted the marginal distribution ct in terms of what would happen if, instead of there being a non-trivial distribution at time t equals 0, we know for sure that at time t equals 0, the state was a specific state x, right? So if that's the case, then this C here would be the matrix with zeros everywhere and 1 in the xth place, right? This says that the initial distribution is described by is degenerate at the xth value, or in other words that x naught is equal to x with probability 1, right? So in this specific case, ct is equal to, and the standard notation for this is delta x, 1 at the xth place and zeros elsewhere, right? So delta x times m to the t. But this is a particularly simple matrix multiplication to evaluate. It is just saying that this multiplication will pick up the xth row from the empty matrix, right? So let's introduce one more name here. So corresponding to the transition matrix M, we were using a stochastic kernel P, right? So this had things like, I could call these rows Px1 dy, that is if the current state is x1, then these are the probabilities, transition probabilities to the different states x1 through xn next period, right? So then, I have a bunch of these row vectors. dy. So corresponding to the matrix M raised to the t, so we haven't shown what we're going to write, but corresponding to this, let's call so we haven't shown that it's a stochastic kernel, but well, in some sense we have, so I'll come back to that. So corresponding to M raised to the t, let's call the quote-unquote stochastic kernel P superscript t. You should not interpret this to be p raised to the t, p superscript t. So I can write the probabilities sitting in the different rows as p raised to the p superscript t x1 dy all the way to p superscript t xn dy, right? And if I have a specific xth row, row x, I can call this p superscript t x dy, right? So harking back to this particular result that ct is equal to delta x m raised to the t, that will therefore be equal to the row p superscript t x dy. Okay. So go back for one moment to this equation, ct is equal to delta x m raised to the t, right? So what is happening here on the left hand side are the probabilities that xt is occupying the different states y, right? And this is saying that those probabilities are equal to delta x times m raised to the t, which is equal to these. Okay, so that tells us that if we take the transition matrix M and raise it to the tth power, so m raised to the t, then in the xth row are the probabilities that starting with being in state x for sure at time t equals 0, that we are in the different states y at time t. Okay, so that's the interpretation of this equation, right? So let's see sort of to labor the point for a little bit more. Let's just see a simple illustration. So let's say I have a two-state world, and let's call those states 1 and 2 instead of x1 and x2, just to keep things very short, right? And my transition matrix M is P11, P12, P21, P22. Okay? So then M squared is very quickly, so unfortunately I'm not editing these videos, so I can't fast forward. So you'll have to bear with matrix multiplication here. So that's equal to P11 squared plus P12, P21, P11, P12 plus P12, P22, P21, P11 plus P22, P21, and P21, P12 plus P22 squared, right? That's M squared, right? So the earlier result will, for instance, tell us that the marginal probabilities of being in different states at time t equals 2, so ct, instead of ct, let's have c2 here, is equal to, so let's say I have a delta 1, so I started in state 1 for sure at time t equals 0, right? So delta 1, so this is just 1, 0, okay, times m squared, right? So that's exactly the first row of m squared. Okay, it's this row. Yeah. And that corresponds to what we know about probabilities of different paths for a Markov chain. That was the main, although extremely preliminary, theorem that we did, right? So what it's saying is, suppose I start at time t equals 0, and then I'm looking at times t equals 1 and t equals 2. So these are my times, and my states are, in each period, the possible states are just 1 and 2, right? So suppose the system is in state 1 for sure at time t equals 0, which is the example here, right? So then what is the probability, for instance, of being in state 1 at time t equals, so this is, state 1, state 2, right? So what is this probability? The probability of being in state 1 at time t equals 2. So this is saying that, look, what we can do is look at the possible paths from state 1 at time t equals 0 to state 1 at time t equals 2. And in this simple two-state world, there are two paths, right? So I go here, and then I go here, or I go here, and then here. Okay? So for this particular event or path of going from here to here and then to here, I just have to multiply the path probabilities, the transition probabilities P11 with P11. So that's just P11 squared. Alternatively, it could be that the state had first gone here, and the probability of that would have been P12, and then that the state would go back to 1. So the probability of that would be P21, right? So in terms of probabilities, that would be P12, P21. So the probability that the state is 1 at time t equals 2, given that the state was 1 at time t equals 0, would be the sum of these two, right? The sum of these two mutually exclusive paths, P11 squared plus P12, P21. And indeed, that is what we have here. And you can work out the others. All right. So one central question for Markov chains would be, well, we have this nice sense of how the marginal distribution evolves over time, right? So one question would be, does it converge to some distribution, or does it not converge? Right. Okay. So we look at that a little bit now. And so you can possibly ignore this sentence here that Ct plus 1 is equal to Ct times m. T going from 0, 1 to blah, blah, blah is a dynamical system. So you may not have encountered this jargon. Dynamical system PSM, what it is saying is that it tracks a distribution evolving on the n-1 dimensional simplex, right? When the evolution is happening using these transition probabilities n. A reasonably okay exposition can be found in one of the early chapters in Stahersky's book, maybe chapter 4 perhaps, right? So I'm saying, okay, it's not that the exposition is not good, it's very good, but Markov chains has lots more in it than this particular chapter deals with, okay? Maybe it's chapter 5 actually. What it's saying about how the system evolves is this. So I have, let's say I have a 3-state world. In general, I have an n-state world. Whatever it is, I can equate any distribution to a point on the n-1 dimensional simplex, right? So suppose this is the initial distribution, C, okay? So using this formula, what is C1, the marginal distribution at time 1? It's going to be C times M, okay? So how can we look at this C times M? Well, so this M is some matrix. For a 3-state world, it will be a 3 by 3 matrix. And this C is the initial distribution. So that's sitting here, right? Initial distribution across 3 states. Instead of x1, x2, x3, let me just call them states 1, 2, and 3, right? So what is this matrix multiplication? It's going to, this probability is going to multiply the first row. Then to that, I'm going to add this probability times the second row. And to that, I'm going to add the third probability times the third row, right? Now, these rows, notice themselves are probability distributions, right? So this is P, let me revert to x1, px1 dy, px2 dy, px3 dy. These are probability distributions. For instance, this one says, given that I'm in state x1, what is the probability that I'll be in x1, x2, and x3 next period, right? So they exhaust all probabilities and they add up to 1. So that's a probability distribution. So because these are distributions, they also all lie on the unit simplex, right? So these are 3 points on the unit simplex. Let's color these points with a different color, right? So these are 3 points. Px1 dy, px2 dy, px3 dy, right? This was my C. It's a probability distribution, sure, so it lies here. But moreover, let me just call these C x1, cx2, cx3. But moreover, you know, this matrix multiplication is just cx1 times this row plus cx2 times the second row plus cx3 times the third row, right? So you can see that this multiplication is nothing but a convex combination of the 3 p distributions, or the 3 convex, or the 3 vectors that lie in this simplex, right? So because the cx1, cx2, and cx3 are probability numbers, that's a convex combination, right? So it's going to lie somewhere here, right, in the convex hull of these 3 points. See? So my C1 is going to lie somewhere here. Okay. So that's interesting, and we can take this places also, but let's not do that. Right now, what we wanted to assure ourselves is that indeed the evolution of the system, the evolution of the marginal distribution is legit. I'm mapping from an initial distribution C to a distribution C1. Okay, so that's a distribution, it's a point here, and then I'll get a C2 being equal to C1 times M. Again, that's a point here. Okay, so that's just using a different convex combination C1 on the same three rows of the transition matrix. So that's also going to lie here, and so forth, right? So what is being said in some sense is that I can view the transition matrix M as a function that picks up a distribution from the simplex and gives me a distribution in the simplex. Okay, so Ct plus 1 is going to be Ct M, and this post multiplication by M, just as pre-multiplication can be looked at as a linear transformation, this also is a linear transformation. The post multiplication by M, what it's doing is it's picking up a point in the simplex Ct and carrying it to a point in the simplex Ct plus 1. Okay, so imagine the dynamics, hopping from point to point in the unit simplex, right? And stability asks, or global asymptotic stability asks a question, for this particular transition matrix M, do these dynamics converge to some single point in the unit simplex or not? Right. So to do dynamics, we will regard this unit simplex P of S as a metric space with the D1 norm. Okay, D1 norm is going to say that we'll come to that. So it's going to take the absolute values of the various entries on any vector or distribution C, right? So the D1 norm, or we can write it as 1. Okay, so that's going to be, suppose this is our 3-state example. So that has a C of x1, you take that plus C of x2, you add them in absolute values. The absolute values are doing nothing for us here because these are probability numbers and already non-negative, right? So you will say, well, why are we really looking at this norm even of taking the absolute values? Because given that these are probability numbers, these are also all going to add up to 1, right? And that's true, they're all going to add up to 1 no matter what distribution you take, right? But this norm also induces a metric, right? So suppose I have 2 different distributions, phi and C, right? So the distance between these 2 points I can evaluate using this norm, right? And that will be phi of x1 minus C of x1 plus phi of x2 minus C of x2, all in absolute values. So I'm taking this particular metric, and we are free to take any of the DP metrics because they lead essentially to the same topology. Let me not say. So the convergence is exactly the same in all these, right? Okay. So we will regard this simplex as a metric space with the D1 norm, right? And we'll say that a distribution C star is stationary or invariant for M if this equation holds that C star times M is equal to C star. Okay, in other words, C star is a fixed point of this system. So C star, if C star is stationary or invariant, what's happening is that post multiplication is like M picking up this point and dropping it back to the point. Okay, so in terms of dynamics, what it's happening is if you start with a marginal distribution C star, you're going to remain there. Or if some dynamical system described by this converges to some C star, then once it is at C star, it's not going to go anywhere, right? So you can also see in the language of fixed points that C star is a fixed point of the map M, right? So C star times M is just C star, okay? So a preliminary obvious result is that every Markov chain on a finite state space has at least one stationary distribution. The idea is I look at the transition matrix as a function, right? So this unit simplex is compact and convex, and this transition matrix as a function, it's just a linear function, so it's going to be continuous. And so I can apply Brouwer's fixed point theorem to say that there is at least one fixed point, C star. What does this say about evolution over time? Nothing necessarily. So now we have the definition of stability of this dynamical system. So when I say dynamical system, it's this first order difference equation of how the marginal distribution evolves over time. Ct plus 1 is a function of Ct given by Ct times M, right? So regarding this as a function, right? So this dynamical system is globally stable in definition, or it's maybe better to say globally asymptotically stable if it has a unique stationary distribution, a unique fixed point C star, and no matter at what distribution C we start, right, the distance between, this is Ct, right? So the distance between Ct and C star goes to 0. Okay, so Ct, in other words, converges pointwise to C star as t goes to infinity. So you can see that this kind of convergence will happen by Banach's theorem if it's the case that this transition matrix M is a uniform contraction, right? Then no matter at what initial distribution C we start, Ct is going to, so I'm getting Ct just by mapping T times with the transition matrix M, right? So that's going to be, if M is a uniform contraction, then that's going to be a Cauchy sequence and it's going to converge, right? Okay. In general, convergence may not happen, yeah. And all we can ensure is that no matter what stochastic matrix M, or no matter what Markov chain we have in mind, this M is non-expansive on PS. So in other words, if I start with two different distributions, C and C prime, and I assess the distance between these two, and then I apply M to both, then the distance between Cm and C prime M is less than or equal to the distance between C and C prime. Okay, what I can't say is that this is a uniform contraction. Yeah, it's going to be non-expansive. And the proof is simple enough, so I will leave it to you to work out. Instead, I'll give a simple example of a Markov process where a Markov process that is not globally asymptotically stable. So consider the Markov process where the transition matrix is this, with the off-diagonal elements being 1, a two-state world with these being 1, right? So how would C, the marginal distribution CT, evolve, right? So suppose I have a, so unfortunately the notation here is slightly different. Let's go back to our notation. So suppose the initial distribution is, in a two-state world, is C of x1 and 1 minus C of x1, right? So then what is CT at t equals 1? So that's going to be C times M. So that's Cx1 1 minus Cx1 times 0 1 1 0, right? So that's going to be 1 minus Cx1, right? So it's just going to switch the probabilities of the two states. And then at time, so as not to confuse with this notation in my lecture notes, I'm going to write these as Ct equals 1, Ct equals 2. By the same logic is going to switch these back, right? So you can say that, if you've done stability in the past, you can say that there is some kind of marginal stability here. The point is there is no asymptotic stability. The only way that this is going to converge is trivially. So if both these probability numbers are half each, then it's going to stay there. And in fact, you can just solve this out and see that the unique fixed point is half-half. But there is no global stability. On the other hand, if you have a two-state world where, so this is again an extremely simple example. So a two-state world in which all these probability numbers are strictly positive. Yeah. So I'm naming them 1 minus A, 1 minus B, A, B, just for convenience. And A and B are strictly between 0 and 1. Okay, so all these are strictly positive numbers. Then you can show that there will be global asymptotic convergence. So one easy way to do it in a two-state or a three-state world is to use eigenvalues and eigenvectors. So just to illustrate, we do that here. So notice that for any Markov matrix, whether two-state or finite state, one of the eigenvalues will always be 1, see? So the idea is that what is sitting in the rows are probability numbers. So each row adds up to 1. And so if I say that I'm going to do the following, I'm going to take a Markov matrix M, and I'm going to multiply that with a vector of ones. Yeah. So let's do it for this example here. Right? So 1 minus A, B, 1 minus B times 1, 1. Right? So that's going to be 1 minus A plus A, B plus 1 minus B. So that's going to be 1, 1. All I'm doing is I'm adding up a bunch of numbers that add up to 1. Right? So this will satisfy that it's equal to 1 trivially times this, right? So one of the eigenvalues is always going to be 1, right? And typically the others will be strictly less than 1 in well-behaved cases. They're going to be less than or equal to 1 anyway, right? And an eigenvector corresponding to the eigenvalue 1 is just ones, right? So we are not even going to go down this route. We're just going to say that, look, one of the eigenvalues is 1. You can easily solve for the other. The other will be 1 minus A minus B. And so these are distinct, real and distinct eigenvalues. So I can diagonalize the Markov matrix M and write it as U times this, so U times this matrix of eigenvalues, lambda times U inverse, where the columns here are eigenvectors. Columns are eigenvectors corresponding to lambda 1 and lambda 2 respectively, right? Okay. And then you know that if I multiply this out several times, so this is M, so what is M squared? It's U lambda U inverse U lambda U inverse. So this will give me the identity matrix. So what remains is U lambda squared U inverse, and this indeed, because it's a diagonal matrix, the squaring is just going to square the elements on the diagonal. So more generally, if I do this T times, I get my M raised to the T matrix is going to be U lambda, the lambda matrix to the T times U inverse, right? So that's pretty useful. If you do this for this two-state case, you will see that I can write the elements of the M raised to the T matrix as follows. So this looks like P11 raised to the T. That's not what is meant here. So it says take any element of M raised to the T, say the first row and first column, call it PT11. Yeah, so maybe it's even better to call it PT within brackets 11. So remember that PT was our notation for the stochastic kernel associated with M raised to the T, right? So I'm saying this is the 1/1th element of p raised to the t. This is the 1/2th element, 2, 1, 2, 2. Okay, so that's m raised to the t, right? You can expand this. You can expand this. You just write down the eigenvectors. You don't even need the actual eigenvectors. Just write this down as, write this down in terms of, a determinant and and that, and carry out the matrix multiplication. You will see that, so for instance, take this first element in the empty matrix. So you will see that it's equal to some constant plus another constant times 1 minus a minus b to the tth power, right? Actually, so this is the second eigenvalue, right? So lambda 2 to the tth power. So what's actually happening is, if you do difference equations, I'm able to write, so in my new notation, this to be equal to lambda 1, which is 1, times a, lambda 1 to the t, which is 1 to the t, right? Plus lambda 2 to the t times b. Okay. I would encourage you to just expand it and see that you can write all of the entries as some constant plus another constant times the second eigenvalue 1 minus a minus b raised to the t. Okay. So let's do this for the first entry, for the 1/1th entry. So let me write this here. 1/1th entry of the empty matrix is a plus b times 1 minus a minus b raised to the t. So then you can see that I can do this for any time t, right? So in particular for time 1, I have, so this by my definition is the 1/1th element of the matrix m, m to the 1, that's just m, right? So it so happens that this is just p11. Okay, remember that my m matrix was p11, p12, p21, p22 was 1 minus a, b, 1 minus b, right? So this is 1 minus a, right? And from this relationship, I have that that's going to be equal to a plus b times 1 minus a minus b raised to the 1. Okay, that's this equation here, right? And again, using this relationship, for the m raised to the 0 matrix, p raised to the 0, 1, 1, what will that be? So for any matrix m raised to the 0 will be the identity matrix, right? So I have made 0 maps using my function n. So if I've made 0 maps, I'm where I am, right? So if I start with any psi, I'll remain at that psi. So the matrix that does that is the identity matrix. That's the identity map, right? So the 1/1th element of that is 1, right? And using this formula, this is equal to a plus b times 1 minus a minus b raised to the 0. So that's just a plus b. All right. So if I solve these out, these are two equations in the variables a and b. I get values for A and B, and I get that, you know, the 1/1th element in the empty matrix is this. And as you can see, as t goes to infinity, it converges to b by a plus b. So similarly, you can see that P12 is going to converge to a by a plus b, right? So very briefly, if I write the 1/2th element of the empty matrix, so as some c plus d times 1 minus a minus b to the t, right? So I'll get that the P1 is c plus d times 1 minus a minus b to the 1, yeah, and that is equal to a, and the P0 from the identity matrix, so that will be equal to c plus d times 1 minus a minus b to the 0, so that's just a 1, right? So from the identity matrix, that's going to be equal to 0. So when I solve these for c and d, I will get that c is a by a plus b, and that's where the convergence will be. And I think d will be minus a by a plus b. So you can work out that starting with certainty in state 1 or state 2 at time t equals 0, I'm going to converge, and therefore in fact starting anywhere at any c at time t equals 0, I'm going to converge to a unique distribution. Okay, so I leave the I leave you to play around with this a little bit, right? So let me end by stating a couple of theorems that talk about global stability in the general case for a Markov matrix. So this is one approach to global stability, and it uses this notion of what is called, what is termed as the Bruschian coefficient of a stochastic kernel P. Right? So what is this? So it's a number between 0 and 1 that we associate with any stochastic kernel P. So I'm going to write out the Markov matrix of this stochastic kernel. So it has these different rows. Yeah, so it'll have some xth row, px dy. Yeah, I'll need some other typical row, let me call it the x primeth row, right? And it'll go all the way down to the xnth row. So alpha of P is the min over every pair of rows x and x prime, yeah, of the following number. That is, you take every pair of rows. So in this particular example, take row x, take row x prime, yeah. For every state y, so suppose this is a state y, you know, the states go from x1 all the way to xn. These are tomorrow's states, these are today's states. For every state y tomorrow, right, you look at the number pxy, the number px prime y, and you take the minimum of these two numbers, right? So suppose this was the minimum, you take the minimum, right? So you hop across all states y and you take these minimal numbers. So for this state, suppose it's this, for some other state it's that, it's this, etc. And then you add up all these numbers. So you can see that when you add up the minimum of all these numbers, you're going to get something less than or equal to 1, right? And you're going to get something greater than or equal to 0. So you do this for every pair of states. You have a number corresponding to every pair of states. And then you take the smallest of those numbers. That's my alpha of P. Okay, so once again, for every pair of states today, for every pair of rows today, you take every possible state that can happen tomorrow, y. You look at pxy, px prime y, and you take the smaller of the two, right? Smaller of the two, smaller of the two, smaller of the two, and so forth. Then you add up these numbers. Okay, you do this, so you'll arrive at one number between 0 and 1 for every pair of states. And then you take the smallest of those numbers. Okay, so for instance, if you do this for Dany-Quaz matrix, that will evaluate to a 0. Alpha of P evaluates to a 0. Okay. What is this exercise telling us? So, take any particular state y tomorrow, and suppose that amongst pxy and px prime y, the smaller number is 0. There's a 0 entry, right? So that's telling us that, suppose we are playing around with this Markov chain and we've started it twice. So let's say at time 0, once we have started the Markov chain in state x, once we've started the Markov chain in state x prime, right? And we have some state y here, right? Suppose the minimum px prime y, suppose that's a 0. That means that if you've started the Markov chain at x prime at time t equals 0, the state will not be y. The state, will not be y at time t equals 1. Whereas if pxy is positive, then the state tomorrow, when you start the Markov chain in state x today, the state tomorrow will be y with some positive probability, right? But will not be y with any probability if you start it at x prime today, right? And so if you ask that what is the probability that these two chains are going to converge at y next period, it's going to be 0. Okay? Whereas if the minimum of these two numbers is positive, that means that this number pxy is positive and so is px prime y. And so if you start the Markov chain at these two different states today, they will converge, they will hop to the same state y tomorrow with some positive probability. Okay? Yeah. So alpha of P is greater than 0, you can show, if and only if for every pair of states today, x and x prime, and corresponding to every two rows x and x prime today, the probabilities px dy in row x and px prime dy in row x prime overlap. So they assign positive probability to at least one common column or one column common state tomorrow y. Okay, so when you're when you're taking the smaller of these two numbers for each column y, right, and you always get something strictly greater than 0, and this is true for every pair of states, right? You always get something strictly greater than 0, meaning, individually for some state y, you may get a 0, but when you add across all these, you're getting a positive number. That means there is some state, call it say y tilde, where the smaller of the two numbers is positive. That means both numbers are positive. That means starting the chain at x or x prime, you meet tomorrow in the state y tilde, okay, with positive probability. So if the Dobrushin coefficient alpha of p is strictly positive, it must be the case that for every pair of states x and x prime, there is some state y tomorrow where the two chains will meet with positive probability. That is, there's some state y such that pxy and px prime y are both positive, okay? So then from any two states at time t, there is positive probability that the chains will meet at time t plus 1, okay? Fine. So the preliminary theorem which associates with this, with the contraction mapping theory is this. It says, suppose P is a stochastic kernel with Markov matrix M, then for every two distributions phi and psi, this is true, that the distance between phi and psi here, when you assess this and you compare it with the following, that you use M to hop from psi to psi M, okay, so think of hopping from an initial distribution to, marginal distribution next period phi M. Think of hopping from initial distribution psi to a marginal distribution tomorrow psi M, right? Then the distance between these is less than or equal to 1 minus the Dobrushin coefficient alpha of p times phi minus psi, okay? And moreover, this is a tight bound. So what this is telling us is that if alpha of p is greater than 0, that is, there is some overlap between every pair of rows, right, then this transition matrix, this Markov matrix, is in fact a uniformly strict contraction with modulus 1 minus alpha of p, okay? There is something strictly less than 1 here, okay? And then you can use Banach's theorem to say that the underlying evolution of the marginal distributions will always converge to a unique fixed point, okay? The system is globally asymptotically stable, right? So theorem 16 in fact says something more. It says, suppose P is a stochastic kernel and M is the corresponding Markov matrix. The dynamical system is globally stable if and only if there is some time t such that the Dobrushin coefficient of the stochastic kernel Pt corresponding to the Markov matrix Mt is greater than 0, right? So this lecture has gone on for too long, so I'm going to close now and I'm going to interpret theorem 16 when I begin the lecture on stochastic dynamic programming.